First, I want to thank Pablo for inviting me on Fridays. Like, Sergio, do you want to give a talk? He's like, sure. So I reused one of the talks I have prepared, so we will see how it flows, how you have questions, if I need to go faster, slower, and then we can go from there. So later I will be around, so you don't, dare to ask questions in public. We can talk later and things like that. So let me start first by explaining a little bit how do I got here. And when I meant here, I meant Google. So I grew up in Madrid, in Spain. I did my bachelor and my PhD in the Technical University of Madrid. And then from there, I went to the European Center for Soft Computing, which is like in the north of Spain, for a couple of years, and then went to UC Berkeley as a postdoc and then as a research scientist. I was lucky enough to be at Berkeley when all the deep learning revolution started happening. So I was part of the Café team who created, this open source code called Café, and then start taking over. People using it for many papers, PhDs, and things like that. And then after a couple of years, I, decided to move to Google to continue doing research and continue contributing to the community. Yeah. So today we're going to talk a little bit about reinforcement learning. And how many of you have heard about reinforcement learning? So hands? Good. That's pretty good. So the main goal behind reinforcement learning is something simple. How many of you remember how you learned how to walk? You remember? I don't remember. It was like, they told me, I wobble around, I try one more time, I fall again, get up, try more times, and eventually, you are able to figure out more or less the coordination, balance, equilibrium, and then you start moving a little bit, not too well, but enough. After a little longer, then you're able to go where you want to go. You say, okay, I want to go to the end of the room, and then you put your mind on it, and you walk. So that's basically a very different type of learning from supervised learning, what is the most common type of learning in machine learning. So we can think of supervised learning is a transformation from more like traditional, what we used to do more like expert systems, you program the system what to do, and now we try to say, okay, instead of programming everything, we're trying to learn from data. But we're going to learn by providing the right answers, what is supervised learning. If you do something well, I tell you. If you do something wrong, I tell you what is the right answer, okay? What happened, that means for every problem that you try, I always need to give you the right answer. And sometimes I don't know what is the right answer. What is the right answer for walking? How do I actually teach you how to walk? If you never walk, how do I teach you? It's very complicated. You have to coordinate a lot of things. You have to feel it. You have to keep balance. It's a lot of things you need to know, and it's hard for me even to explain what it means to walk. So the idea behind reinforcement learning is instead of trying to provide labels for every single case and give you the right answer, then I'm going to do it by trial and error. You're going to try, you're going to fail, I'm going to try again, and sometimes you're going to do better. I'm going to tell you, good job, keep going. If you do badly, I say, not so good, try again. So I'm going to provide some kind of reinforce with some kind of reward. Something like it tells you when you're doing well, but I'm never going to have to tell you what is the right answer. I'm just going to give you either positive signal or negative signal without having to provide what is the right answer. And that enables to solve many more problems that supervised learning sometimes cannot solve. On the contrary, you also have a lot of other problems because it's much harder to learn when you don't tell me what is the right answer. You can think in something like that, There's many different kinds of learnings, and you can see more like the traditional learning, you go study, memorize until you really know the answer. When you don't know, they tell you the right answer, and you study again until you know the answer. Versus a kid was people sometimes reinforce you, but it's mostly trial and error. You just play around trying to figure it out by yourself. And then you have some motivations, some intrinsic motivations, some external motivations. Luckily, over the last few years, reinforcement learning have been applied to many problems, going from recommender systems, data set encoding, robotics, chemistry, physics, or little robot in the middle, and AlphaGo that our folks our friends in DeepMind, solve using reinforcement learning. So the main change is like we're going to change a little bit the paradigm in like supervised learning. We're going to have some kind of observation coming from the environment of the task. Our model is going to generate some actions we're going to apply in the environment, and then based on that, it's going to get some reward and more observations. Sometimes you're going to do well. In the case of like breakout here, you're going to move the paddle. You're going to try to hit the ball. When you break one of these bricks, you get points. When the ball drops, then you lose points. And by interacting with this environment, you're going to basically learn the rules of the game and what it means to win and what it means to fail. So when we try to apply some of these problems to apply RL, many of these algorithms to our problems, we realize there's a lot of pieces that you need to implement actually to make this work. There's a lot of more libraries and tools for supervised learning available, but not so many for reinforced learning. So when we started working on this a couple of years ago, we realized having all these tools in place is very useful. So we start creating these tools for our own research in Google, and many people start using inside Google, and then we also decide to open source this code. So then for people who are starting with reinforced learning, they have some places to get all these pieces. So that's what the idea of these TF agents came about. Is basically, can we build a library basically to make it easier to use reinforced learning and to do research or apply to solve real-world problems? So you can go on GitHub, you can download, you can pip install it, and start playing around. So the main idea is we want to make it reliable because reinforced learning is very unstable in general. So there's many bugs and many things that make it hard. So we want to make it sure that the code is very well tested, very well designed, and we can trust what we're doing. So when the instability happens, it's because the algorithm of the task is difficult and not because we introduce bugs into our own code. And we're still discovering some from time to time. But at least we have all tests, benchmarks, and all those things to basically highlight when there's a problem happen. The other part is we wanted to create a lot of as a learning tool for people who are maybe new to RL, who are maybe want to give it a little try. So we have a lot of collabs, samples, tutorials, documentation to make it easier. But also we want to be able to apply to complex problems. So people who want to apply into their production system can take our code, take the pieces that they need, and start solving problems. For example, like some game companies are applying to their production system to recommend games and other things. And then the other part we use also is when you want to develop new algorithms in RL, you want to be able to compare to the state-of-the-art algorithms to decide to modify how to make it better. And as I mentioned before, we try to make it very well tested, easy to configure, and easy to modify. So at the beginning of this year, when TensorFlow was working into the release of TensorFlow 2.0, we said they have really nice features to make it RL more flexible because it doesn't fit into this common supervised loop that, get the data, compute the gradients, apply the gradients, and iterate, because there's a lot of other things you need to do on the place. So having this flexibility for eager mode and TF functions make it much easier to develop new algorithms. We made it also compatible for 1.15 for the people who are still not ready or they have also, legacy code that they want to use it. But what we make is also, very easy to add new tasks or new problems, in this case, like different suites, either OpenAI Gene Environments, Atari, Mujoko, DeepMind Control, PyBullet. It's easy to add new environments to these things, so you can try and apply these algorithms to your own task. Also, we also implement many of the state-of-the-art algorithms, ranging from the classical DQN, double DQN, RNN DQN, C51, DDPG, TD3, PPO, Sofactor Critic, and many others. And we also, keep implementing more. We also take contributions from outside for people who will say, oh, I have these algorithms, I would want to, make it available, or new papers where people, develop on top of TF agents, and then they start releasing their code. And then, as I mentioned before, we try to make it, keep very good test coverage, make sure, we have regression tests, so these algorithms keep performing as they should. We have caught many times changes in the underlying implementation, maybe a TensorFlow or something, make a regression in our own implementation. Okay, this thing used to work, now it's not working as well, and we don't know why, and we have to see what's happening. So this is an overall view of like the whole system, very simplified in some sense. But basically, like the main part what changed from supervised learning is a collection. You need to collect new data. You need to do this notion of like trial and error. So when you learn something, you go to try again and apply it to the problem, and then you collect fresh data. So this notion of like collecting fresh data all the time. So we need to be able to handle that part. We're going to use some replay buffer to reuse the data, and then there's going to be the training happening, what is more similar to the supervised learning, but it's very specific. It could be multiple optimizers, multiple ways to, sometimes you use gradients, sometimes you don't use gradients, maybe you use algorithms, and other times to update your model, but then you collect more data and keep going. Let's focus a little bit in the environment case. We mentioned before this breakout environment. The main thing you need to define is basically, what kind of actions can I make in this environment? My model needs to decide, okay, can I move to the left or can I move to the right? So basically, you need to define the possible set of actions. And then when I start playing, I may need to play again because I, get stuck. So I need to reset. And then I only need to apply an action to the environment and get some observation and some reward. So basically, this is the high-level, API of these environments. So once you define an environment, we make it simple to define a policy. It could be hand-coded, it could be learned, it could be wherever you want. But basically, the idea that you're going to interact with this environment, play. At the beginning, maybe it's a random policy. You don't do very well. You just do random actions to see what happens. And eventually, you will get better and better by playing this game. To make it faster, we also scale the data collection by doing in parallel, so you can play the multiple games in parallel at the same time to make it a lot faster to learn. And the main, this collection part, we provide some tools to make it a little easier how to collect the data, how to handle all these, like, play the game, restart the game, and all those things that need to happen so you can keep learning, collecting data as fast as you can for the training. So we define these wrappers to make it, many of these environments are not part of TensorFlow, and we don't want them to be part of TensorFlow, so we have wrappers to make it accessible from TensorFlow and make it faster. We have these replay buffers to make it, collect the data and all those things. And then we have this driver that basically drives all these pieces together. For the training part, once we have some data, we're going to basically, at the end, try to learn some policy, usually a neural network, smaller or bigger, but basically it's going to say, the idea is you're going to have some observation, and you have to decide what actions you're going to make. Usually it's going to be multiple networks, not just one. Some of them will be a critic, some of them will be a value network, some of them will be an actor network. But at the end of the day, the part that interacts with the environment is going to be something that assign different probabilities to different actions. So you're going to say, if I'm here, maybe more likely to go to the left than to the right. And then your model is going to learn and modify those things as you learn to perform better over time. You can define your networks using Keras models, Keras layers, and basically put it all together with your network, in this case, DQN agent, replay buffer, and basically iterate as more like a normal loop. But remember, at the same time, you also need to collect data in parallel. So this is the main overall view of like all the pieces back together in some sense. And now I'm going to talk a little bit like for other cases where you don't need all like the assumptions that RL need to make. There's a simplified case where it's these multi-arm bandits that another person talked today, where it's also very useful for recommender systems, or many things that you have multiple solutions that you can choose, and also make it easier to train and all those things. So for example, in the case of like recommending movies, let's suppose you want to recommend one of these movies to the users, and there's some probability that they will like it, but you don't know a priori how much they're going to like the movie or not. So you can do different things. You can propose, what you think is the best movie, and everybody will watch the same movie, and some people will like it or not. Or you need to do some exploration to basically understand what is the preference of the users. So there's going to be some trade-off between exploration and exploitation. What's going to happen at the beginning, you need to learn what they prefer, and later you can optimize for what they like. So the main difference between RL and bandits algorithms is like the action of the agent doesn't influence the next state of the environment. Basically, there's and every single point in time, you can basically start from scratch and make your own decision without having to think what are the decisions you make in the past or what decisions you're going to make in the future. But in RL, all those things make a difference because when I'm walking, if I move one leg, I need to move the other leg, and they have to be coordinated. What I do now is when I influence the features. So for the simplified case, it doesn't matter. In so many cases, you can do this simplification, and then there's many other algorithms you can do because of that simplification. In the past, many people will do this A/B testing. Like basically, you will say, "Oh, I'm gonna assign different possibilities to different users, and then at the end of the testing, I'm gonna decide what is the best, and then basically assign that to everyone." And what happened, like while you are still figuring out what is the best action, basically many people not gonna like what they see. So it's what this called disregret. Basically, your model is basically recommending different things for people who don't like it, but you don't know yet until you finish this testing. And then the idea of this multi-arm banding is like you basically, as you learn, you basically change your recommendations. So you do that trade-off between exploring and exploiting. So basically, you get to the optimal solution quicker, and then you basically need to run less experiments to get what is the optimal solution. And here is like a simple graph. It's like how many recommendations do you need to do until you figure out what is basically the best solutions to this problem. And comparison, A/B testing, epsilon gridding, and some more complicated model like quantum sampling, where you basically have an estimate of the uncertainty. So basically can know how much do I know about the user before recommending, should I explore more, or should I exploit in that case. So recently we add many of these algorithms to TF agents. So for many problems, I usually tend to people is like, you are gonna try the problem, you can even try another algorithm first before trying RL. First, because it's more stable, it's easier to train, it's easier to reason about, and sometimes you get a good enough solution. Sometimes the sequential aspect of it is really important for the problem. Like for example, in this breakout, the sequence of actions is important, and so at some point you will want to move to the RL algorithm. We also provide some of these environments to people to test their algorithms and compare to the ones we provide, and a lot of metrics that you can compute to know how well are you doing. So going back to this movie recommendation, there's this movie lens data set that basically, you try to solve, you can solve using, matrix factorization and a few others to basically collaborative filtering, or you can use some bandit algorithm to solve this problem. And then here you have comparison of different algorithms, like how, the models learn and perform depending on different strategies. You use linear models, neural models, drop out of some samplings, and more advanced models give you to better solutions quicker because you have a better estimate of the uncertainty. So many of these things you can apply to recommender systems when you have to recommend different options to different users. And this is some roadmap that we have for TF agents, other things coming up, like new algorithms, leaderboards, new tools like distributed collection, distributed training, multi-GPU, TPUs are kind of coming soon, and new environments, for example, Unity. So the team is so a lot of people who can contribute to this software to make it happen and to be able to open source and release. And you can visit that, GitHub, as I mentioned, use some collabs and minitars. And then I would recommend trying this DQ carpool or this soft therapeutic minitar so you can see, it takes some time, but you can see how this little robot learns how to walk. For ending, I also want to highlight some other people who are using TF agents to make their own research. For example, in robotics, at Google, many people start using to solve some of these tasks, for example, navigation, locomotion, and things like that. And then you're starting, simulation, like these physics simulators, and then you want to translate to the real robots. Here's one example of one of these robots navigating around the Google offices, and basically avoiding obstacles, avoiding people, and this model is basically trained first in simulation, in like a modular simulation of like buildings, and then it's transferred to the real robot and basically can navigate around. It can, remove, if the path is blocked, it can go around, turn around. If there's someone, get in front of you, will trying to avoid collisions with people. And there's a lot of, open problems in this area, how to do, multi-agent systems, so considering other options, other robots or other humans in the thing, how to make it very safe, so you don't want to, during the exploration, to make mistakes. And this is another one which is more translating to the real robot, what is the locomotion and the walking, and basically how you basically avoid some of these obstacles too, but also how you can transfer some of these death estimation and things like that from the simulators to the real robot, so the robot can actually navigate and avoid these obstacles at the same time that it's learning how to move. One more problem that I want to highlight, because my colleague Stephanie is presenting a poster on Saturday in the Deep RL workshop. As I mentioned before, many of these algorithms are unstable, and it's hard sometimes to know what's going on. So we are proposing some metrics, to be able to compare all these different algorithms across different characteristics, like how stable is to train, how reliable, how much can I trust them? Can I trust them in the short term? Can I trust them in the long term? Are they going to forget what they learn, or they're going to be easy to tune, or going to be very hard to tune? So there was in 2017, there was a paper that basically analyzed different algorithms. And for example, in this case, it was if I run the same algorithm in the same setting 2 times, I get very different results, statistically different results. So the difference between these 2 runs is they are basically the random seed. There's no any other difference between these 2 runs. On the right, there's you can see the bands and confidence interval we compute for many of the tasks in different algorithms, in different tasks. And you can see in some cases very narrow, but in others it's very wide. So not all the algorithms are at the same level of stability. And here we actually ran some statistical analysis according to these metrics, across time, are you going to have forgetting in the long term, in the long term on those things, and compare different algorithms, not only in the performance, but also how reliable they are. So then you can decide, okay, I want to choose the most performant algorithm, but it's maybe very unstable, or I prefer to choose a more stable algorithm that maybe doesn't get to peak, but I can tune easily, I can rely on it, it's going to work for many different tasks, and it can generalize across tasks. Finally, I want to highlight some of the opportunities for people who are looking for research internship in the next summer. I think there's opportunities all over Europe, America, I think Pacific also. Big C on the back can guide you more. But here is some of the links that you can apply for Google Research in 2020. It's already open. So I think it's closing soon, so you are interested, apply. And then another program that's also open is this Google AI Resident Program. This is a more longer term. It's 12 to 18 months for people who are basically want to work with some of their asks at Google and do some research, for people who are want to do a deep dive and get much more expert published papers and get to collaborate with many of the researchers at Google. And finally, if you have questions or comments, I will be happy to answer some of them, or later when we mingle around. Thank you.